See how many we need. We'll do as many as we need. Let's start with some easy ones. I know I keep saying there is nothing easy in this book. Okay, on page 308. Page 308, let's start with any preference. Let's start with 38 on 308. So we have limit as x approaches 0 from either side, from e to the x minus e to negative x minus 2x, everything divided by x minus sine x. I see a limit, I see a ratio. Of course, I have to test it. So let's test it. E to 0 is 1. E to 0 is 1. 1 minus 1 is 0. Negative 2 times 0 is 0. So then the top is 0. I'm hoping what? That the bottom is also 0, because there is no hope otherwise. Oh, it's 0 if it's something else. Okay, so 0 minus 0 is 0. Perfect. Limit as x approaches 0. Conditions are fulfilled for L'Hopital's rule. I have a limit. I cannot apply this procedure for any function unless there is a limit, right? I can never differentiate the top and differentiate the bottom unless I calculate a limit. It's a ratio, and I have 0 over 0 or infinity over infinity. Otherwise, I will never use this procedure, ever. Okay. So then the top prime will be e to the x. E to negative x prime will be negative e to negative x, but multiplied by negative 1, the inner function prime, minus 2 over 1 minus cosine x. Is this okay so far? So e to the x prime is e to the x, but e to negative x prime is e to negative x times the inner function prime, and minus 2 over 1 minus cosine. I will have to clean it up a little bit. So limit as x approaches 0, e to the x plus e to negative x minus 2 over 1 minus cosine x. I have to test again. I don't know how to proceed. I have to test. 0, this is 1. With 0, this is 1. 2 minus 2 is 0 again. And cosine 0 is 1. 1 minus 1 is 0. So this is like starting all over with a different function. It's a limit, it's a ratio, it's 0 over 0. I will apply L'Hopital's rule. Okay, limit as x approaches 0, the top. E to the x prime is e to the x. E to negative x prime is negative 1 times e to negative x. And the denominator is positive sine x. 1 prime is 0. Negative cosine prime will be sine x. Okay, I test again. The top is 1 minus 1, which is 0. The bottom is sine x, sine 0, which is 0. As if I start from scratch with another function. Limit, ratio, 0 over 0. Limit, x approaches 0. The top, e to the x prime, e to negative x prime is positive, e to negative x. And I hope that this is the last step. Where does the top go? Perfect. Where does the denominator go? 1. So finally, the limit is 2. And I just promised the simple one, right? It looked good. Now, the more difficult situations are when we do not get 0 over 0 or infinity over infinity from the get-go. So these are more difficult. This is a product, this is a product, this is a product, This is a difference. This is a difference. This is a function raised to a function, which are the most difficult ones. Function raised to a function. All these are functions. So from 55 through 66, we have to do at least 2. And let's start with that and then come back to others. Any preference? Which one? 66. This one? Okay, perfect. It's okay if it's on the checklist, I don't mind. So if it is. 66 on page 308. So this is limit as x approaches infinity from 2x minus 3 divided by 2x plus 5 and everything raised to 2x plus 1. Well, this is a mess, right? But first of all, it rings a bell. And it was the first problem on our second test. I see a function raised to a function. What was the procedure that we had to think about or apply immediately? The log. So keep that in mind. Okay, now I have to test. First of all, I have to test and see what this is. Okay, but that's the idea behind a function raised to a function. So when x approaches infinity, what type of rational function is this? 2, true. But we discussed those 3 types. Awesome. Yes, you can determine that limit, but I just want to refer back to those. Type 1. What would be the horizontal asymptote? Because this is what I'm asked to find. What happens when x is infinity, positive infinity, what will this function do? Where will it go? Exactly, which is 1. I can show that by simply taking the limit and applying L'Hopital's rule. The derivative of the top is 2, the derivative of the bottom is 2, so the limit will be 1. So this whole piece will approach 1 when x approaches infinity. But where will this power go? Right. This is one of the 7 indeterminate cases. I would say one of the ugliest. Maybe I should say better, one of the most difficult ones from the 7. Products are easier. Difference, we have one difference. Ratios are nice, especially if it's 0 for 0, right? Infinity over infinity. This is the ugliest. Okay, good. So I know I cannot conclude. The answer is not 1. This is an indeterminate case. And then, how do I start? Right, but I have to write that y equals 2x minus 3 over 2x plus 5 raised to 2x plus 1. And remember, I cannot bring down the power unless I do something to both sides from the very beginning. If I only do it to this side, it's wrong. Very good, awesome. So then I can write natural log equals 2x plus 1. If I omit to put parentheses around 2x plus 1, I make a huge mistake. And natural log of 2x minus 3 over 2x plus 5. Okay, so what did we do? Not much. We denoted the function by y. We applied natural log to both sides. Now I want to apply what to both sides? Yes. You can say, wait a minute, but this is exactly what we did when we differentiated it, right? We used the tool of log, and then eventually we differentiated. Here I use the tool of log, but now I really want to find the limit. But you can say, wait a minute, you're not asked to find the limit of a natural log. You're asked to find the limit of this function. We will get there. Like we did with applying natural log and then differentiating both sides. The same thing here. We applied both log to both sides. Now we have to apply the limit to both sides. Same idea. So I will apply limit to this side as x approaches infinity from natural log y. And I will apply limit as x approaches infinity to 2x plus 1 times natural log 2x minus 3 over 2x plus 5. And very soon, not in the next 5 minutes though, but soon we will get rid of that log. And we will definitely find the limit of the function. Now I have to test again. I have no choice. I'm hoping that it's no longer 1 to infinity. I hope that I change it into a product now. From a power, indeterminate case power, from to a product. Let's see. When x approaches infinity, where does this go? Awesome. Very good. Where does this go? But careful, we have to do it in 2 steps here. The limit as x approaches infinity of this is, careful, we differentiate 2 over 2, which is 1. And then natural log of 1 is?
0.
Very good. So we did accomplish something. Now we no longer look at a power, but we look at an indeterminate case, which is 0 times infinity. We cannot conclude yet. Okay. So I will continue in the hope that in the next step, I change it into 0 over 0 or infinity over infinity. That's my hope. Okay, now, I don't want to take this anywhere because it's log. If I bring it down, it will be log to negative 1. I don't want to touch this. My only hope is that I will flip this. Here's how. Limit as x approaches infinity. At the top, natural log of 2x minus 3 over 2x plus 5 over, what should I write so that when I flip it, I still get the 2x plus 1 in front? Of course. That's it. I changed the presentation of the function, the way it looks, but I did not change the actual function. Okay. I test again. This is very clear, right? I don't have to test again this because I already have the answer 0. What about this? Where does this go? Bless you. If it doesn't go to 0, then I'm not on the right track. It goes to 0 because it's 1 over, it's type 2, right? Type 2 meaning the horizontal asymptote must be 0 as x approaches infinity. Okay, now I'm in business. It's a limit, it's a ratio, it's 0 over 0. What do I do? Yes, apply L'Hopital's rule. I recommend at this stage to first replace this using a property of log, because I really don't want to differentiate the ratio, but it's not a problem. How do I change this? Perfect. Yes, that's easier to handle. And how do I change the denominator so I don't have to use a ratio?
It's negative power.
Yes, 2x plus 1 to negative 1. Awesome. So this was an intermediate prep in which I used the property of the log. Thank you both. And I changed the denominator into, so it's easier to differentiate. Now I have limit as x approaches infinity. The denominator changes into negative 1 times 2x plus 1 to negative 2 times the inner function, which is 2 prime, which is 2. And the numerator changes into 1 over 2x minus 3 times 2 minus 1 over 2x plus 5 times 2. I would like to factor out a 2 and simplify it with a 2 in the denominator. Would you allow me to do that? So you can write 2 outside and find the least common denominator for the top. And 2, negative 2, and 2x plus 1 to negative 2, so I can simplify these two. What is the least common denominator in the numerator?
The product of the
Yes. 2x minus 3 times 2x plus 5. So the top of the first function gets a 2x plus 5, and the top of the second function gets a 2x minus 3. Is this okay? Should I write it again? It's not clear. It may not be super clear. I'm so sorry. I can write it again. Jason, is this okay? Please say no if it's not, please. So, is the derivative clear? 1 over 2x minus 3 times the inner function prime minus 1 over 2x plus 5 times the inner function prime. I pull the 2, it's right here. This and this factored out. And this 2 is in front. So I can simplify it. And then the least common denominator is the product of these two. So that's why the 1 needs the other one that it does not have. And this 1 needs the other one, 2x minus 3. So then 2x plus 5 minus 2x plus 3. 2x plus 5 times 1 minus 1 times 2x minus 1 times negative 3. Is this okay? Okay. So limit as x approaches infinity. Negative in front, so I don't forget about it. So the top is 8 divided by 2x minus 3 times 2x plus 5 times, if I flip this, 2x plus 1 squared over 1. Although it's still ugly, much more human. Okay, so there is a negative 8. And now I'm asking myself, when x approaches infinity, this is a rational function, what type? 1, 2, or 3?
Type 3. No.
If it's type 3, it means that the degree of the top is by 1 unit larger than the degree of the bottom.
It's not.
I always hope for type 1 or 2. So what is the degree of the top?
It's type 1.
2. Very good. What is the degree of the bottom?
Same 2.
2. What would be the first term here if you expand 2x plus 1 squared? What would be the first term? Awesome. What would be the first term here when you expand it? So what is the limit as x approaches infinity from all this?
1.
Do you all agree with 1? So then the limit is negative 8. And you can say not so fast. It's not done. Now I go back 5 pages earlier and I copy the beginning of our calculations. And I copy the end of our calculations. So we had limit of natural log y equals negative 8 when x approaches infinity. There is a theorem that I warned you about a long time ago in which I said, if this function is continuous, I'm allowed to do this. Swap the operators. This is an operator called natural log. This is another operator, limit. We applied natural log to both sides. We applied the limit to both sides. They're both operators. So we can swap only if this function is continuous. Yes, this function is continuous. It's a continuous function on its domain. So then, and definitely at infinity, there is no discussion. So I swap the operators, and I have natural log of the limit of our function as x approaches infinity equals negative 8. And now, final step. What can go in here so that the natural log is negative 8? Can I put 5? No. Can I put 10? No. What should I have in here so that the answer is negative 8? it must be something with the power with the base of e. Raised to, exactly. So I can bring the power in front, and natural log e will be 1. So we found the limit. This is what we're looking for. We found that the limit as x approaches infinity from 2x minus 3 over 2x plus 5 raised to 2x plus 1 is e to negative 8. I will not put a problem like this long on a test because yes, it took me 10 minutes or more because I needed to explain and talk to you about each step, but I don't want you to have any problem that exceeds about 10 minutes at the most on a test, because then I don't test anything else. So let's summarize and then choose one more. Here's the summary. We had a function raised to a function. Every time we look at a function raised to a function, we will have to involve log. We have no choice. So we denote the function, we apply log to both sides, then we apply the limit to both sides, we calculate the limit of the log, at the very end we get a number, we copy the first step and the last step, and then we swap the operators to find the limit. Ready? So let's choose something like 57. Now this time I would like you to walk me through the steps. So limit as x approaches 0 from 1 minus 2x raised to 1 over x. We determine the limit for the most difficult one. Okay, so this cannot be that hard. I observe that it's a limit from a function raised to a function. I have to test. So when x approaches 0, where does this go? Right. I don't like it from the beginning, right? So when x approaches 0, this is either infinity or negative infinity. So it doesn't matter. This is an ugly situation. So then what do? Yes, I denote the function by y. That's my first step. In second step, I have to apply natural log because it's a function raised to a function. So natural log y equals 1 over x times natural log 1 minus 2x. In step 3, I apply the natural log operator. Now I need to determine or apply to both sides what? The limit operator. So limit as x approaches 0 from natural log y must equal limit as x approaches 0 of natural log in parentheses 1 minus 2x over x. I have to test again. What do you hope for? Since it's a ratio.
0,
Or,
okay.
exactly. So let's plug in 0. What do we get at the top?
We get natural log of 1, which is 0.
Perfect. What do we get in the denominator?
0.
Perfect. After solving that most difficult one, now this looks like a piece of cake. Okay, so then limit as x approaches 0. The top is over and multiplied by negative 2 and divided by. Perfect. So now let's rearrange this. Its limit as x approaches 0 from negative 2 over 1 minus 2x. I test again, and I hope that it's done. What do I get? when x approaches 0. This approaches -2. I will copy the beginning and the end. Are we in agreement with -2? Because this disappears, it's 2 over 1 with minus in front. Agreed? Okay then, so I copy limit as x approaches 0 from natural log y equals -2. I copy the beginning of step 3. If you want, we can call this step 4. So I copy the beginning and the end. What will I have to do next? Yes, knowing that under certain conditions of continuity, I am allowed to swap the operators. So in step 5, if you want, I will say natural log in parentheses limit as x approaches 0 of y is -2. And there is only one number that this can equal to. That's it. That's it. So I will write finally that limit as x approaches 0 from 1 minus 2x raised to 1 over x is indeed e to -2, or you can write e squared. And these are the most difficult situations because there are, as you see, 5, 6 steps. One more time, it's a function raised to a function. I denote it by y. I apply natural log to both sides. I apply the limit to both sides. I determine that limit of natural log, and then I copy the beginning and the end, and I swap the operators, and I identify that that limit must be e to -2. There is no other number. Only natural log of e to -2. I bring -2 in front. Natural log e is 1, and I get -2. Is this better? Do you think we need more examples with L'Hopital's rule? Yes? Let's choose. Of course, products will be more difficult, right? Ratios will be easier. Products, we encountered the product. It took us 10 minutes, right? So ratios. So let's do 49. Let's do 49 because we have not seen a ratio like that, a difference. So in 49, we have limit as x approaches 1 from x over x minus 1 minus 1 over natural log x. You would probably say, or someone would probably say, well, separate. I can't. I cannot apply the limit to this minus the limit of this. Because if you remember, the limit law requires that this exists. The limit of this does not exist. And the limit of this does not exist. It's 1 over 0. So I can separate. So what is my only chance? To find what? What will you do to a subtraction of two fractions? Yes, you will find what first? Perfect. So this must be x minus 1 times natural log x. The first one needs a natural log x, and the second one an x minus 1. So what will you say about the numerator?
X natural log of x minus x minus 1.
Very nice. Good. Plus 1. Okay, now I can test. I plug in 1. Where does the numerator go? I certainly hope for either infinity over infinity or 0 over 0. That's my hope. The numerator goes to?
0.
Perfect. And the denominator goes to?
0.
Perfect. Natural log 1 is 0, x minus 1 is 0, 0 times 0 is 0. Nice. So I can apply L'Hopital's rule, but I have to be very careful because I have a product here and I have a product here. So the fact that we are allowed to differentiate the top and differentiate the bottom inside the limit that is 0 over 0, it does not waive us from using the product rule when product rule is applicable. Okay, so x prime is 1 times natural log x plus x times natural log prime, which is 1 over x, and then minus 1. Now the denominator prime, first one, is 1 times natural log x plus x minus 1 multiplied by 1 over x. Let's take a moment and check this. So x prime is 1 times natural log x plus x times natural log x prime minus x prime. Now these are two functions. The first function prime is 1 times the second plus the first function times the second function prime. So far so good? Okay. Now I noticed something, that this x with this x will go away, and this is positive 1 minus 1. I like this. These two go away. So then limit Sx approaches 1 from natural log x at the top. The denominator has natural log x. Now I have to distribute, and I have positive 1 minus 1 over x. I distributed 1 over x to x, and I got 1. And I distributed 1 over x to negative 1, and I got negative 1 over x. Is that okay? I have no choice, but I have to test again. The top goes to very good. The denominator goes to, this is 1 minus 1. Okay. Still have hope. Okay. Limit Sx approaches 1. The derivative of the top is 1 over x. The derivative of the denominator is 1 over x plus 1 over x squared. Because 1 over x prime is negative 1 over x squared, but with minus in front will be, I don't want to do anything anymore. I want to find the top where it's going, which is 1, and I want to find where the denominator is going, which is 2. And this is it. And we had to apply L'Hopital's rule twice. 1, 2, 3. Questions on L'Hopital's rule? Questions on graphing?
I do have a question.
Please, James.
Earlier.
Yes, any question.
Oh yeah, the 2x, so limit of 2x minus 3 over 2x plus 5. I was, as x approaches infinity.
Very good. So since it's infinity over infinity and it's a ratio, inside the limit I can apply L'Hopital's rule.
Oh, that's good. Okay.
So the numerator prime is 2, the denominator prime is 2, so the answer is 1. Or, I remember that this is type 1. Every time I try to determine the limit as x approaches infinity from type 1, it's always the leading coefficient over the leading coefficient. But you don't have to memorize that, because now we have L'Hopital's rule and we can always determine. Very good question. Anything else? Anything else? Anything else?
More of a curiosity question.
Yes, yes.
Can you essentially have any function become slant asymptote, or like, can you have?
So the problem that we just looked at, we simplified it, right? And that was already the difference, that the quotient was already the slant asymptote. But it does not, I cannot change a function into its asymptote. So the answer is no.
I guess I'm thinking like, could you have x cubed as an asymptote for another?
No, an asymptote means a line.
Okay.
So it cannot be a quadratic, it cannot be cubic, it has to be a line.
Okay.
So when we talk about an asymptote, it has to be a line. It's either horizontal or slant. That's why only type 3, only if the degree of the top is exactly by 1 unit larger, higher than the degree of the bottom. If it's degree 4 over degree 2, that function does not have a horizontal and does not have slant. Only if the quotient of the division is linear, which requires 5 over 4, 10 over 9, 2 over 1. Only those give us a quotient that is a line. If the quotient is not a line, it does not have a slant asymptote. Okay. There are 2 more sections from this chapter. One of them deals with a very big and vast topic, huge topic, called optimization, meaning finding max min for different situations. And this is a topic as big as the related rates. As you see, it starts here, and look at all these types of problems. We can spend a month just on this section, which we can't. So let's just start by looking at an example. So this is a major application of calculus, optimization. So this is section 4.7. What is that? So finding max min of different situations, of different functions, with applications in real life situations. Yes, it's not a super easy situation. Why? Because most of the time I will not be given the function. Like we were not given the relation between functions at related rates, right? We had to come up with an equation, some relationship between those functions. They were all functions of time, or most of them functions of time, but we had to find a relationship between the two of them. That was not given to us. The same kind of difficulty we have here. We are given a situation, but we are not given the function that we need to maximize. We have to find it, or minimize, for that matter. Okay. So I like to look at a problem like 9 for now. On page 332. I am hoping that you are working on the checklist. If you have any difficulties, please bring them on Thursday. So I'm hoping that you can finish 4.1 through 4.5 between now and Thursday, if possible. Or at least look at the problems and say, I think I'm going to need help with this or that. Okay? So we can discuss those problems. Okay? Because I'm thinking that the checklist should be due a week from Thursday, if we finish. Not this Thursday, the following week. And you also have this extra credit and the quiz for Monday. Not Monday, for Tuesday next week. So I think we didn't get this, right? So this is for test 2 and the quiz. And they are both due next Tuesday. And Nick, where is he?
Oh, he dropped the class.
He dropped the class.
It's gonna be tennis.
Okay, problem 9. A model used for the yield, so Y is yield, Y, of an agricultural crop as a function. So model used for the yield Y of an agricultural crop as a function of the nitrogen level N in the soil measured in appropriate units. So N is nitrogen. Okay, here's the function. Y equals K times N divided by 1 plus N squared, where K is a positive constant. Fine. What nitrogen level gives the best yield? What does that mean? What are we asked to find? Maximum of Y. Exactly. In other words, find max for Y. Awesome. How do I find the max for Y? What do I have to determine based on what we know? Very good. I have to find Y prime. The variable is uppercase N. K is a constant. Because it's a constant, I don't even want to see it. Because it's a factor of the top. It can wait. This is a ratio. I need to differentiate this. It has a constant that will stay outside. The top prime is 1. 1 plus N squared minus the top times the denominator prime. Very good. Over 1 plus N squared squared. Very good. I will clean it up. K outside. 1 plus N squared minus 2N squared over 1 plus N squared squared. Combine like terms. K can wait. Negative N squared plus 1 over 1 plus N squared squared. Of course, I'm going to pull out a negative, K, and write N squared minus 1 So now I'm asking myself two questions. Are there critical numbers coming from Y prime being undefined? No. N squared plus 1 is always positive, not 0. Are there critical numbers coming from Y prime being 0? It's a fraction. The top is N squared minus 1. So there are two options. N can be and N can be. The nitrogen level can be yes, so 1 and negative 1. Well, we're not talking about nitrogen level of negative 1. So this is the only critical number, 1. So I will put 0, I will put 1, 0, and I will study the sign of the derivative. Because I have to show that this critical number changes into a maximum. If I can show that n equals 1 changes into a maximum, then it's not a maximum. So let's take a look at the function. I hope you agree that I will definitely not worry to plug in anything in k times n divided by n squared plus 1 squared. So it would be a waste of time. So now I would like to plug in 0 to check this side. If I plug in 0, what do I get? Yes, with the minus in front. So it's positive. What if I plug in 10? I have this 100 minus 1 with minus in front. What is this? So now it's guaranteed that this is a maximum. And I can say y when n is 1 will be maximum. Absolutely. And I can go back and plug it in. And I have k divided by 2. And this is guaranteed to be the maximum.